go. Newton's first law. We've got the law of inertia. I'm going to write the names of each of these on the bottom edge of my tab that shows. It's actually not even a Sharpie. It's a Papermate Flare pen. They are the best. Yes, they are. They're from the 80s. So, first law, the law of inertia. I'm going to leave the top blank for a second, and we're going to add something there. We are writing our definitions on the back, which I realize means that you might have to drive off the cliff edge of your notebook if your tab goes to the top. I care a lot. No, it's okay. You'll figure it out. So, the law of inertia says the following. Objects at rest. You already know this. Stay at rest. Objects in motion. Oh, Lane. Stay in motion. Gets weirder and weirder in here every day, doesn't it? Objects at rest, stay at rest. Objects in motion, stay in motion. Now, this isn't always true because there's an unless. You can feel it coming, right?
How do you write that?
Unless they experience an unbalanced force. Oh, that's not how balanced is spelled. Balanced force. I'm going to add a couple things to this definition here. Here's our basic definition. Objects at rest, stay at rest. Objects in motion, stay in motion, unless they experience an unbalanced force. Objects are made of matter, right? So what are we talking about? Oh, that's good. Yep. We're saying, anytime we say the word object, we're talking about mass. If something is at rest or in motion, those are constant velocity situations, right? So what those things mean is constant velocity, either velocity 0 or some other number. And this unless means that at that point they would experience acceleration if they experience this unbalanced force. I'm going to add a really important word here, which almost counts as a separate vocabulary word. It's the word net. Not internet. Net force. What does the word net mean? Yeah, it means total. So a net force, it's like your net income, your net worth. Your GPA is like your net grade in some ways, okay? It's hopefully not 0. We should talk if it's 0, all right?
How are you in this class when it's 0? That's
There's always hope. All right. So, you right now stay at rest in your seat. If your lab partner shoves you, you will accelerate out of your seat. Objects that you move. So you shove your lab partner. Newton's first law says they will continue at constant velocity to stay in motion. Why does your lab partner slow down if you shove them out of their seat?
The ground.
They interact with other objects. They experience air resistance. There is a net force. There is a total of other forces acting on that object that results in another acceleration back to 0. If we were to go to outer space and you politely shoved your lab partner out of our space station classroom, they would continue in motion at a constant velocity, which means magnitude and direction, forever. In discussion with your partner, on the front, I want you to draw a doodle that represents the law of inertia. Go.
Motion diagram.
This is perhaps our most used of the three laws, and it's the one that has a mathematical explanation. So, Newton's second law, let's focus out one more time there, because the 2 looks really blurry. Okay, nope, that's as good as it gets. Newton's second law is the one that is mathematical. I'm going to write it a bunch of different ways. It all says the same thing, okay? Net force is equal to mass times acceleration. If you say F equals ma, you are wrong. Just like saying weight and mass are the same. It's not that F equals ma, a net force equals a mass times acceleration. You'll see this written other ways. You'll see it like this. What does that fancy thing mean? Yeah, so that's the Greek letter capital sigma. It makes the S sound. It makes the S sound even though it looks like an E because it means sum. So it means add together all the forces. That equals the mass of that object times the acceleration. Could you do algebra and write this a different way? Yes, you totally can. So, on the back of my tab. The acceleration of an object. We've been measuring acceleration a lot up until now. The acceleration of an object as produced by a net force is, and here are your very important terms, directly proportional.
Excuse me.
You just want to get it on the YouTube video. That's what's happening here. The acceleration of an object is produced by a net force is directly proportional this isn't going to fit in here. I misread the line. I was like, make sure I get it right. To the magnitude of the net force comma, and inversely proportional is a word I can't spell unless I think about it one letter at a time. Proportional to the mass of the object. So we've got some math terminology in there. Directly proportional and inversely proportional. What does directly proportional mean? There's a direct relationship. Yep. Good paraphrase. If I drink more coffee, what happens to my mood? I get happier. So I increased the amount of coffee I had. It increased my mood. That's a directly proportional relationship. The two variables increased in the same direction. If I decrease the amount of coffee I have, what happens to my mood? Unhappy. It's a directly proportional relationship. When I change one variable in that negative direction, the other variable is influenced in the negative direction as well. What do you suppose inversely proportional means? When one thing goes up, the other thing goes down. Okay? So, the more coffee I have, the less stress I feel. The less coffee I have, the more stressed I feel. I shall sip some coffee. I am.
Yes.
So, I'll point out right here that the way we phrased this definition doesn't start with force is equal to. That's because it is often more useful to think about what we can observe, which is the motion. The acceleration is the thing we can measure and observe. So I'm going to add one more version of this equation on the front based on those words I just wrote. It said that acceleration is directly proportional to, that means those two things should be equal, and inversely proportional to the mass. This is just the algebraic rearrangement of this, right?
Yes.
But this is sometimes a very useful way to look at it. Don't just look for a net force. Observe an acceleration. All right, you've got 1 minute. Draw a doodle on the front with your shoulder partner. Sort of a sidebar. But when we think about that unit for force, we said it is a Newton, right? So force is equal to mass times acceleration. What's the unit for mass? Times acceleration, meters per second squared. That's why a Newton is equal to a kilogram meter per second squared. When I said that yesterday, you were all like, what? You're just making stuff up now?
Yeah.
But that unit, no, that frequently is the case. That unit is a summation of this, right? It's just an abbreviation for kilogram times meter per second squared, because we have meters, or we have mass times acceleration. Newton's third law on the bottom. It's often called the action-reaction law. That's not really an official name for it. None of these really have an official name except the first one, the law of inertia. What I want you to think about summing this law up as is this is the forces come in pairs law. All right, this is the forces come in pairs law. Okay, so on the back of my tab, and I realize that pink one's kind of hard to see on the big screen, so sorry about that. For every action, there is an equal and opposite reaction. By action, what do we mean?
Acceleration.
Acceleration is the effect. It's the thing that we can observe. But if you take action, you can't just manifest acceleration, but you can exert a force. So action means force. For every force acting on an object, there is an equal and opposite reaction. So, you are sitting on your chair. That's a picture of you. That's right. Yeah.
Oh my goodness.
You are sitting on your chair. What are the forces that are acting on you? Okay.
Oh no.
Gravity. You all broke your oath already. What's acting on you?
You agree with that?
Okay.
The force of gravity. I'll abbreviate that force by using a capital F for force, and I'll put a little subscript G for gravity. So, we've got this downward force, but why aren't you accelerating towards the center of the earth right now? There's something stopping you. There is an equal and opposite force pressing up on you from your chair. This is called the normal force. And it's normal because normal means perpendicular, so it's not because it's ordinary or everyday or it's the regular force. Okay? So, there is an equal and opposite force exerted on you by the surface you're interacting with. Okay? All right, you got 1 minute. Turn to your neighbor. Make a doodle on the front that represents forces coming in pairs.